Hello, F block. We are going to take a look at section 5.5 about other exponential and logarithmic functions as your cumulative review for this week. I chose this section for you to learn on your own because after the beginning part, I think it's fairly straightforward. This is also not a huge deal in terms of stuff we absolutely need to move forward, not a very large focus on the AP exam. But I do want to show you how to deal with other exponential functions and other logarithmic functions besides the natural log of x and e to the x. The first thing we're going to take a look at is a process called logarithmic differentiation. For example, I'd like to take a look at the very strange looking function y equals x raised to the 2x, and I want to find dy dx. You know about the power rule, but the power rule only works if the power is a constant. It won't work with a variable thing there. You know about the e to the x rule, but that only works if the base is e, not if it's, well, anything else, in particular if it's a variable. Variables in the base and the variables in the power, you don't have a rule that's going to work, and in fact, there is no rule that really works for something like this. Instead, there's a process that we can follow called logarithmic differentiation. So to deal with this, well, I'm not going to write down we need logarithmic differentiation, but that's what we're about to do. As the name suggests, there will be logs involved. Specifically, the only log you know about at the moment is the natural log. So I'm going to start by taking the natural log of both sides, and then I'm going to do some simplifying. Step number 1, I'm going to take the natural log of both sides and simplify. Which means I'm going to get the natural log of y equals the natural log of x raised to the 2x, which I feel like took something complicated and made it look even more complicated. What is the advantage to this, though? What am I now allowed to do? Well, what I'm allowed to do is related to the end of that, simplify. Now that I have that natural log there, I can take that power and I can move that power up front. This is not calculus, this is log property stuff. And I can turn this problem into 2x times the natural log of x. Next, now that I have this and I no longer have a power inside, like a variable power for something that was a variable, I have a product instead, I can handle doing the derivative. But because I don't have y equals, instead I have the natural log of y equals, I need to use implicit differentiation. Step number 2, we are going to go and we are going to differentiate implicitly. Derivative of the left side equals the derivative of the right side. What's the derivative of the natural log of y? And be a little bit careful, please. Well, natural log of y should be 1 over y, but remember, implicit differentiation here, x is the independent variable, so I need the whole chain rule thing, multiply by the derivative of y, which means multiply this by dy dx, 1 over y, dy dx. Please take a moment and find the derivative of the right-hand side, which will require the product rule. Send in the derivative of the right-hand side once you have it. First, times derivative of the second, plus second, natural log of x, times the derivative of the first is 2, and I should clean that up a little bit. So let's say this is 2 plus 2 ln x. Now, I need to go and solve for dy dx. And when I'm done, I'm going to figure out a way to give an answer just in terms of x. Solve for dy dx and give the answer just in terms of x. Okay, so I'm going to multiply both sides by y, and I'm going to get dy dx equals y times 2 plus 2 ln x. However, the original problem was an explicit function, y equals something with x's in it, which means my derivative should only have x's in it, shouldn't have a y in there. Any idea what I could do to get rid of that y and get an answer just in terms of x's? We can replace that y with what it was initially. What was y? Y was x raised to the 2x. So we can say that dy dx equals x raised to the 2x times 2 plus 2 ln of x. And we have found the derivative. What was the point? This is now a formula that would find the slope of that original function anywhere. What you need to know is this process is useful when we have variables in our base and in our power. This method, maybe not just useful, why don't we say used, is used when we have variables in the base and the power. I'll make the video pause so you can get caught up on anything you might need. Okay, I would like you to try one. Let's see here. Oh, you know what, never mind, I'm just going to another page. Okay. Y equals the sine of 3x raised to the x squared minus 2. Take the natural log of both sides and simplify. Natural log of y equals the natural log of the sine of 3x raised to the x squared minus 2. The point of that was so we can take that power and move it out front. So I'm going to get the natural log of y equals x squared minus 2 times the natural log of the sine of 3x. Please find the derivative of both sides. I'm going to find the derivative of the left. I'm going to find the derivative of the right. What's the derivative of the left? 1 over y, dy dx. On the right, okay, so I need product rule. First times derivative of the second. First is x squared minus 2. Derivative of the second, well, this looks like chain rule to me. In fact, looks like a 3-part chain rule thing. Take care of your natural log. You get 1 over the sine of 3x times the derivative of the sine. Okay, derivative of sine is cosine 3x times the derivative of what's inside there, so times 3. Plus second times derivative of the first. Natural log sine 3x. And I'm going to multiply that thing by 2x. I just want to show that the 2x isn't inside the natural log. Let me do some cleaning up. 1 over y dy dx equals, how about we say 3 times x squared minus 2. I can make that a little nicer. Cosine over sine will give me a cotangent, so cotangent of 3x plus 2x times the natural log of the sine of 3x. Take just a moment, finish it off. Yes, it's going to be ugly, but that's what it is. And again, this is the formula that finds the slope of that original function. dy dx equals y times 3 x squared minus 2 cotangent of 3x plus 2x times the natural log of the sine of 3x. Replace the y with what it was. Dy dx equals the sine of 3x raised to the x squared minus 2 times 3 x squared minus 2 cotangent of 3x plus 2x times the natural log of the sine of 3x. And that mess is my derivative, is the final answer. I will not make these much uglier than this. This is not a super important topic, but it is something we're going to need for a few things later today in this video. I'm going to pause this to make sure you're all set, and when you are done, please get out that packet that's labeled Pre-Calc Review of Exponential and Logarithmic Functions. Okay, so part of the reason we did this is because this is part of stuff that we're going to need to deal with other exponential and other logarithmic functions. What is an exponential function? Anything in the form f of x equals a constant to the x. So technically what we had just been looking at, they weren't exponential functions. Whatever. Exponential functions in the form 2 to the x, 10 to the x, 1/2 to the x. Logarithmic functions are in the form f of x equals log base a of x, like log base 2 of x, log base 10 of x, log base 1/2 of x. And you definitely spent time on this in Algebra 2 and a little more in pre-calc, probably more time than you spent with the e to the x and the natural log stuff. We're not going to spend much time on graphing, but how do you graph something like this? 2 to the x will plug in values. Plug in 0, 2 to the 0 is 1. 2 to the first is 2, 2 to the second is 4, and so on. Logs are inverses of these things. So 1 comma 2, the inverse is 2 comma 1. 3 comma 8, the inverse point would be 8 comma 3, and so on like that. My domain for my exponential becomes the range of the log, and so on with the range of the exponential becoming the domain of the log, and all of that stuff. There's a horizontal asymptote there, there's a vertical asymptote there. I think all you really need to know is any exponential function has a basic shape that looks like our e to the x, and any logarithmic function has a basic shape that looks like our natural log of x. A few properties of these things. This is sort of our inverse property idea. Y equals a to the x has a similar meaning as x equals log base a of y. So here's the deal. 2 to the third equals 8. Of course it does, because 2 times 2 times 2 equals 8. If I'm dealing with things in this form, it's like my 8 is my y, my a is my 2, and my x is my 3. If I write this in log form, my a becomes the base of my log, a. The thing inside becomes my y, the thing over there becomes my x. I think this is way more complicated than it needs to be. 2 to the third equals 8, of course, because 2 times 2 times 2 equals 8. The way that I talk about this when I teach about logarithms in Algebra 2 is I say that logarithm problems ask the question, what is the power? So this power problem has a related log form, log base 2 of 8, which is asking the question, 2 raised to what power gives you 8? The answer is 3, because I know that from what I have over here. Although I think we could have just figured that out, actually asking ourselves the question, 2 to what power gives us 8? The power is going to be 3. Next example, I know 81 to the negative 1/2 is 1/9, because remember 81 to the negative 1/2 is 1 over the square root of 81. Square root of 81 is 9, so 1/9 over there. The related log problem is going to be log base 81 of 1/9 equals negative 1/2, which is asking the question, 81 to what power gives us 1/9? Answer is going to be negative 1/2. So, we're going to do some evaluating with some logs. Number 1. Oh, wait a minute. Is there a typo on here? Did I forget to put the base of that log? Or can you tell me anything? Hopefully you remember from Algebra 2 and Pre-Calc, if there is no base, it's what we call a common logarithm, which just means the base is 10. The way you're going to think about this is you're going to ask yourselves the question, 10 raised to what power gives us 100? And what is that? The answer is 2. I'm hoping this is looking fairly familiar. Please take a moment, do 2 through 10, and send the answers into Edpuzzle. Log base 4 of 16. 4 to what power gives us 16? 2. Log base 5 of 125. 5 raised to what power gives us 125? 3. Log base 9 of 9. 9 raised to what power gives us 9? 1. Log base 8 of 1 is 8 raised to what power gives us 1? Well, we know that anything raised to the 0 gives us 1, so the answer is 0. Log base 2 of 1/8. 2 raised to what power gives us 1/8? Well, to get a fraction, you're going to have a negative power. Negative 2 to what power gives you 8? 3. so negative 3. Log base 3 of 1/3. 3 to what power? Equals 1/3. Negative to move to the bottom of a fraction. 3 to the first power gives you 3, so negative 1. Log base 9 of 3. 9 to the what gives you 3? I think it's a square root, so we're going to say 1/2. Log base 16 of 2. 16 to what power gives you 2? I think that needs to be a 4th root, so our power is going to be 1/4. Finally, log base 25 of 1/5. 25 to what power gives us 1/5? Well, it needs to be negative. 25 to what power gives us 5? Square root, so a 1/2 power, and our answer is negative 1/2. Number 2, logarithms and exponential functions are inverses of each other. We know that the natural log and e to the x are inverses, but a to the x and log base a of x are also inverses, which means if you put one inside the other, they cancel each other out, just giving you x. F of g of x is x, g of f of x is x. Definition of things being inverses. Go back to the 5-3 notes if you need some more with x. Next, we have this thing called the change of base formula. Because most calculators don't have an easy way of finding like log base 8, they have a log button, which really means log base 10, and an ln button, which means log base e. But for other types of logs, we can use this change of base formula that says if I want to do log base a of x, I can evaluate this in terms of any other type of log. I can say this is log base anything, let's call it b of x divided by log base b of a. The one that's going to be most useful for us, since we've done the most work in here with natural logs, is trying to write everything in terms of natural logs. Log base a of x is the natural log of x divided by the natural log of a. For example, if I want to do log base 8 of 15 on the calculator, well, you can use this change of base formula to say the natural log of 15 divided by the natural log of 8. Type that in, 1.303, which means 8 to the 1.303, hold on, 8 raised to the 1.303 is pretty close to 15. It's not exact because I had to do some rounding there. Notice that unlike our properties of logs that say when we subtract, we divide the stuff inside, I'm not dividing the stuff inside. I'm actually dividing the natural logs here. Log base 2 of 50, natural log of 50 divided by the natural log of 2. We're going to use the inverse properties in our change of base formula to do some equation solving. On the next page, I want to solve an equation that looks like this. I'm going to show you 2 ways to do it. If I want to try to use my inverse properties, which is probably how you saw it in pre-calc, but probably not how you saw it in Algebra 2, we can undo a 5 raised to the something by taking the log base 5 of both sides. I can take the log base 5 of 5 raised to the x minus 3, and on the other side, the log base 5 of 3,125. The reason I did that is because log base 5 and 5 raised to the anything are inverses of each other, and they cancel each other out, just leaving us what was in the power. We're going to get x minus 3 equals log base 5 of 3,125. Take a moment. Go to your calculator. Use your change of base formula. Tell me what log base 5 of 3,125 is. Oops. Natural log of 3,125 divided by the natural log of 5. Oh, actually, it's really nice. I'm just getting 5 there. X minus 3 equals 5, so x equals 8. This is how we can use our inverse properties to do this. You maybe saw a different way in Algebra 2. In Algebra 2, we usually teach it as, let's take this problem in exponential form and rewrite that problem in log form. We can say log base 5 of this thing over here equals the power. Log base 5 of 3,125 equals x minus 3, and then go from there. We already know that that log is 5. 5 equals x minus 3. Solve, you're going to get x equals 8. Number 6. I have a log. How can I undo a log? By doing 3 raised to both sides if I'm using my inverse properties. 3 raised to the log base 3 of 2x minus 5 equals 3 raised to the 4th. The reason I did that is so I can make the 3 and the log base 3 cancel out, giving me 2x minus 5 equals 3 to the 4th. 2x minus 5 equals 81. 2x equals 86. X equals 43. Again, if you don't like this, the way you would have seen this in Algebra 2 is you would have rewritten it in exponential form. 3 raised to the 4th equals 2x minus 5, and then you can solve from there. and get x equals 43. I'm going to make the video pause so you can get caught up on anything, and then we're going to do some notes on derivatives and integrals. Okay, so I need my notepad back. And my notepad went where? Here's my notepad in the printer. Okay, so the reason we kind of went through all this stuff, the pre-calc review, the stuff in the beginning, is so we can deal with other exponential and logarithmic functions. We're going to start with other logarithms. I want to find a formula that would let me do the derivative of log base a of x. We know how to do the natural log of x, but now I want a formula that would find the derivative of log base 2 of x. Well, the trick is in our change base formula. Why don't we write log base a of x as the natural log of x divided by the natural log of a? And actually, I'm going to do a little more rewriting here. This, first of all, so I'm using change base formula to get this. Natural log of a, though, that's just a constant because a is a constant. So how about I kind of say this is the derivative of 1 over the natural log of a times the natural log of x. And again, this is a constant. Well, my constant multiplier rule says this is 1 over the natural log of a times, what's the derivative of the natural log of x? 1 over x. The point of all of this is I now have a formula that says the derivative of log base a of x equals 1 over the natural log of a times 1 over x. This is my formula that I can use to find the derivative of log base 2 of x, log base 5 of x, log base 17 of x. I think I have like 2 or 3 examples of this to show you. First of all, a very straightforward one. The derivative of y equals log base 5 of x. There is nothing fancy that I have to do here. I have a formula. All I have to do is plug things in there. My derivative is, 1 over the natural log of a, 1 over the natural log of 5, times 1 over x. I suppose I could make it look a little nicer and say 1 over x, ln 5, but either of those would be okay. Y equals log base 4 of 2x minus 3, a little more involved. What rule will you have to use to be able to find the derivative here? Hope you said chain rule because there's something inside. Let's start by doing the derivative of log base 4. Derivative of log base 4 is 1 over the natural log of 4 times 1 over the thing inside. By chain rule, though, we're now going to go and multiply by 2. I could say 2 over natural log of 4 times 2x minus 3. I would need the parentheses to show that the whole thing is getting multiplied by the natural log of 4. Could switch the order, put the 2x minus 3 out front, something like that. One more. Y equals log base 3 of the square root of x minus 1. Another chain rule problem. Unless you have a way of dealing with that square root. Any ideas of a way we could rewrite this problem so I wouldn't have to deal with the square root inside my log? Well, the properties of natural logs that we looked at apply to any sort of logarithms. In fact, you learned them in terms of any sort of logarithm. Why don't we apply that here and say that our original function is just 1/2 times log base 3 of x minus 1. It's going to make it easier to find the derivative. Take a moment, go find the derivative, please. I'm leaving my 1/2 out front. Derivative of log base 3 of something is 1 over the natural log of 3 times 1 over the thing inside by chain rule times 1. And put it together in one big fraction. Let me say 1 over 2 ln 3 times x minus 1 or something kind of like that. You can make the 2 a power inside there, whatever. This is how we can do derivatives of other logarithms. Next thing we're going to look at other exponential functions. Other exponential functions. The derivative of a raised to the x. I'm going to try to create a formula for this. I know the derivative of e to the x is e to the x, but a to the x, a little more involved. Well, here's how I can do this. Let me rewrite the problem as y equals a to the x. And what are we doing? We're going to find y prime. What can we do? Well, remember the beginning of this video when we talked about that logarithmic differentiation stuff? Of course you do. I can use that process to find the derivative here. What's the derivative? Well, actually not the derivative. Let me go and take the natural log of both sides. Why am I doing this? So I can take that power and move it out front. What's the derivative of the natural log of y? 1 over y, dy dx. But as for this part, natural log of a, that's just a constant. This is really a constant times x. What's the derivative of a constant times x? Just your constant. Dy dx equals the natural log of a times y, or we can say dy dx equals the natural log of a times a to the x. That is my formula that I am now going to use for finding the derivative of an exponential function. The derivative of a raised to the x is the natural log of a times a to the x. I honestly think the trickiest part of this stuff is remembering the formulas, because by the time we're done, we're going to have 3 total formulas. They are going to be very similar to each other, which makes memorizing them a little bit tricky. First thing you're going to do, let's do an easy one first. I'd like you to find the derivative of 4 to the x. Again, you just have a formula, plug things into the formula, send the answer into Edpuzzle. My formula says the derivative is the natural log of 4 times 4 raised to the x. What if we have this? What if we have y equals 5 to the 2x cubed minus 4x? What rule are you going to have to use here? I hope you just said chain rule. Take a moment, find the derivative, just make sure you're careful with your parentheses. Okay, take care of the exponential parts. Natural log of 5 times 5 raised to the 2x cubed minus 4x. But by chain rule, I now need to multiply this by, and we need our parentheses here, 6x squared minus 4. That's it. These are not going to look super pretty. It's fine. What's the point of this? I just found a formula that would tell me the slope of this function over there. One more. Y equals 6 to the x times x to the 6th. What rule do we need to use here? Hope you just said product rule. Take a moment, see if you can use the product rule, and when you're done, maybe factor out the GCF. And when you're done, send in your answer. First, 6 to the x times derivative of the second, 6x to the 5th. Normal power rule on that. Plus second, x to the 6th, times derivative of the first. Well, what's the derivative of 6 to the x? Natural log of 6 times 6 raised to the x. Looks like I could take out, what can I take out? I can take out a 6 to the x, and I can take out an x to the 5th, and I can make this x to the 5th times 6 to the x. You're left with a 6 and an x ln 6. That would be your simplified derivative. One more thing. Integrals. The integral of a to the x dx. If I want to find what has a to the x dx as my derivative, it's going to be 1 over the natural log of a times a to the x plus c. Why? Find the derivative of this thing. Here's a constant out front. What's the derivative of a to the x? Natural log of a times a to the x. The natural logs cancel, we get a to the x. This is our formula for integrals. For the rest of this video, you are not to think about chain rule, product rule, quotient rule. Our trick with integrals is usually use substitution, except in a problem like this, where you're just going to straightforwardly use your formula. Please go find the integral of 3 to the x. Send in your answer. My formula right away says 1 over the natural log of 3 times 3 to the x plus a constant. Sure, you can put the 3 to the x up top. I'm done. I'm just going to leave it. Something like this. X cubed times 6 to the x to the 4th minus 2. We need to do a u substitution here. Tell me what u is, and then tell me what du is. U is going to equal x to the 4th minus 2. Its derivative is 4x cubed dx. We can make this work. Stick a 4 inside and a 1/4 outside. This becomes 1/4 times the integral of, okay, so here's my 6 to the u. This whole other thing is my du. Integral of 6 to the u du. Finish the problem. Okay, let me put that in there. Guess I could have moved that up top, but whatever. Should look something like this. 1 over 4 natural log 6, sure, you can make the 4 a power if you want, times 6 raised to the x to the 4th minus 2. At the end, don't forget your constant. Last one that you're going to do. Go do it and send in the answer. U is the tangent of x. Du is the secant squared of x, dx. Everything works out nicely, so we can say this is the integral of 2 to the u du. Well, that's 1 over the natural log of 2 times 2 to the u plus a constant. So 1 over the natural log of 2 times 2 to the tan x plus c. And we have our integral. I do not have any intention of making the derivatives and the integrals harder than what we just saw here. We have done way more complicated use substitution things, chain rule things, product rule things. There's no need with these things. Really, the whole point is, do you know the formulas, and can you apply the formulas to things like product rule, quotient rule, chain rule, use substitution, and that. Final thing I want to do is just get all the formulas in one place. Yes, these need to be memorized. You will need these for the test. I find these to be the 3 hardest formulas to remember because they're so similar. You need to know that the derivative of log base a of x equals 1 over the natural log of a times 1 over x. You need to know that the derivative of a to the x equals the natural log of a times a to the x. You need to know that the integral of a to the x dx is going to equal 1 over the natural log of a times a to the x plus a constant. These are our 3 new rules. You need to keep track of, is it the natural log of a, or is it 1 over the natural log of a? And then is it 1 over x, or is it a to the x? Of course, on your test, I won't just make you apply the formulas directly. You'll also have to do the chain rule, product rule, quotient rule, use substitution stuff like we did in the examples here. For the rest of this assignment, you do have the homework stapled to your cumulative review and all that. We will go over this in class on Thursday, February 17th. If you do want the extra point on your cumulative review, that assignment will need to be done as well by Wednesday the 16th, submitted to Google Classroom. Otherwise, just show it to me in class on the 17th for regular credits.